Hi, my name is Murphy Liu, majoring in biomedical engineering at Bucknell University. I'm here to present my research on deep brain stimulation for Parkinson's disease. Deep brain stimulation is an established treatment option for movement disorders. It involves implanting electrodes deep into the brain and stimulates specific regions with electric pulses. For Parkinson's disease, the stimulation target is the subthalamic nucleus, also known as Stim, which is structure involving motor control. To predict the amount of tissue activated by the stimulation, computational models can be used. These models often incorporate the tissue anisotropy, which defines as the direction of the brain conductivity. However, how brain anisotropy will affect the VTA, the volume of tissue activation, is still unknown, particularly at individual patient level. The goal of this project was to investigate the effect of local change in tissue anisotropy on the size and shape of the VTA in a patient-specific manner. 40 patients who received bilateral STM-DBS surgery participated in this study, which resulted in 72 implantations in total. The tissue activation models incorporated patient-specific electrolocalization and brain anisotropy were built using the finite element approaches. To account for local change in brain anisotropy, the tissue activation was built for each contact. In addition to anisotropic models with uniform brain conductivities in all directions were built for comparison. The metric used to evaluate the size of the VTA was volume. Isotropic VTA volume was found to be significantly larger than that of isotropic VTA across all the patients. The isotropic VTAs were classified into three groups based on their relative location to STM. However, none of those groups show significant difference in VTA volumes. Sphericity was used to assess the shape of the VTAs, ranging from 0 to 1, where 1 corresponds to a perfect sphere. The sphericity of isotropic VTAs was significantly lower than that of isotropic VTAs across all the patients. Isotropic VTAs were grouped based on their location relative to the STM. Dorsal VTA were found to have higher sphericity, suggesting that more isotropic tissue conductivity than those centered around or ventral to the STM. Overall, incorporating isotropic tissue conductivity has significant effect on the size and shape of the VTA. This effect varies based on individual patient's tissue conductivity and VTA location relative to the STM, suggesting that isotropic tissue conductivity should not be ignored in patient-specific VTA model. Thank you for listening.